Let's derive an equation which relates the pressure, temperature, volume, and amount of an ideal gas, often called the ideal gas law. Such an equation is called an equation of state. We will make the following assumptions. An ideal gas consists of atoms that do not interact with each other and bounce elastically off of the walls of the container that the gas is in. This means that the velocity of an atom only changes when the atom hits a wall, and the kinetic energy after hitting the wall is the same as the kinetic energy before hitting the wall. We will use the following equations from physics in our derivation. The distance that an atom moves is its velocity times the time it moved. When an atom hits a wall, it experiences a force equal to the change in momentum of the atom divided by the time it takes the collision to occur. Due to Newton's third law, the wall experiences a force of equal magnitude in opposite direction. The pressure on the wall is the force on the wall due to the atom divided by the area of the wall. We assume that there is no preferred direction of motion, so that the average velocities in the x, y, and z direction are equal. This means that the average velocity squared in the x direction is 1/3 the average velocity squared in an arbitrary direction. Since there are no interactions between the atoms, the total energy is just the kinetic energy. We assume that the thermal energy corresponding to each degree of freedom is 1/2 kT, where K is Boltzmann's constant. This comes from the equipartition theorem and is too hard to prove. We will take it as the definition of temperature. I may prove it in a later video. In our case, atoms can move in the x, y, and z directions, and thus have 3 degrees of freedom. Therefore, the average energy of each atom is 3/2 kT. Finally, the universal gas constant R is Avogadro's number times Boltzmann constant, K. Now let's derive the ideal gas law. Imagine a cubical box whose sides have length L. A single atom of mass m and velocity v sub x is bouncing back and forth in the x direction. Let's compute the time it takes for the atom to hit the same side of the container twice. First, write the relationship between distance, velocity, and time. The distance the atom travels between hitting the same side twice is equal to the velocity of the atom times the time between hitting the same side twice. Divide both sides by v sub x to get the desired time. Now, the atom has to travel a distance 2L between hits, since it has to cross the box twice to return to the same side. We need to compute the average force that the atom exerts on a given side of the wall. We use the subscript 1 to refer to the fact that there is only one atom in the box, and the subscript x to refer to the fact that the particle is only traveling in the x direction, so it only exerts a force in the x direction. Since the atom is changing direction when it bounces off the wall, it must be accelerating, and therefore the wall must be exerting a force on it. The force the wall is exerting on the atom is the change in the atom's momentum divided by the time interval in which the change takes place. Since we want the average force, the time interval we use is the time between successive collisions of the atom with a given side of the container. Newton's third law says that since the wall of the container is exerting a force on the atom is also exerting a force on the wall with the same magnitude but opposite direction. Thus, the absolute value of the average force on the wall due to the atom is the change in momentum of the atom divided by the time between successive collisions of the atom with a given side of the container. We have already calculated the time between collisions. To find the change in momentum, note that the atom reversed direction but didn't change speed when it hit the wall, so the change in momentum is twice the momentum that it has before and after the collision. By definition, pressure is force divided by area. We just computed the force due to one atom bouncing back and forth in the x direction, and the area of the side of the box that is being hit by the atom is just L squared. Bring the L to the denominator. In the prelude, we showed that the squared velocity in the x direction is 1/3 of the squared velocity in an arbitrary direction. This allows us to write the pressure in terms of velocities in arbitrary directions. We drop the subscript x because now we allow the particle to move in any direction, and so it exerts a pressure in any direction that it happens to be moving. So far, we have only derived an expression for pressure due to one atom. If the ideal gas contains n atoms, the pressure is just n times the pressure due to one atom. We will drop the subscript 1 because from now on our formulas refer to the pressure of an ideal gas within atoms. The volume of the container is just L cubed. Multiply and divide by 2. By definition, the kinetic energy of an atom is 1/2 mv squared, and since the energy of an ideal gas atom is pure kinetic energy, the total energy of an ideal gas atom is 1/2 mv squared. According to the equipartition theorem, the energy of an atom with 3 translational degrees of freedom is 3/2 kT. 2/3 times 3/2 is 1. Multiply both sides by volume. The number of atoms in the gas is the number of moles of gas times Avogadro's number. The universal gas constant is Boltzmann's constant times Avogadro's number. This is the way the ideal gas law is normally expressed. Pressure times volume equals the number of moles of gas times the universal gas constant times the temperature.